Hello and welcome to 2021's first DevOps for Everyone event. In this episode, I was joined by Arthur Bussa of French company Padok. Arthur talked to us here about writing Kubernetes operators and why you should be doing it too. Arthur is one of Padok's site reliability engineers who specialize in Docker, Kubernetes, AWS, and GCP. So let's jump in.
The goal of this talk is for me to share my experience writing a Kubernetes operator, and I'm going to try and convince you that writing an operator might be something you want to do as well. So for starters, who am I? My name is Arthur. I'm an SRE at Padok. We're based in Paris, in France, and I'm also a certified Kubernetes administrator. So my job is to build scalable, performant, and reliable systems on top of Kubernetes. And so the point of this talk is to talk about a Kubernetes operator, but what is a Kubernetes operator? And I think CoreOS introduced the concept 4 or 5 years ago and gave a great definition, which you have on screen. And the idea is that an operator is a piece of software that knows how your application, how your stateful application, but how your application works, and it is able to operate it. So a lot of operators already exist. You have operators to run Postgres inside Kubernetes. You have operators to run Prometheus inside Kubernetes. You have plenty of operators, and people are starting to write their own for their own applications. And this is exactly what we did. So before I get into what the operator does and how we built it, let me start with why, because I think it's important to understand that we were actually trying to solve a problem that Kubernetes itself could not already solve. And so the project we were working on, we had a cluster full of workers, and so each worker was a pod. So if you don't know what a pod is, it's a server that we can send requests to so that it performs some form of work. And so we had plenty of different types of workers, which had different capabilities and different needs. Some required GPUs, some didn't. Some required more CPU or more RAM than others, etc. And these workers, they passed data around. We'll call these documents. So the idea is that, for instance, you have the blue worker sending data to the green worker processes it, sends it to the yellow worker, processes it, sends it to the red one, then the gray one, then the purple one. And the purple one, the last one in the chain, usually stores the resulting data somewhere in a final database. So the first worker in the chain, the blue one, usually extracts the data from somewhere, and the purple one stores it. So it's basically like a really big ETL pipeline. So it's very flexible, and the pipelines are on demand. We have users who tell us, well, I need to process this data with this type of worker, and then this type of worker. So we need it all to be very dynamic. So let's take this diagram we have right here and simplify it a little. This makes things much clearer. And what you need to know is that each pipeline is basically streaming in data. So it has a frequency, basically the number of documents we're sending per second. So in this example, let's say we're sending 10 documents per second through this pipeline. That's a metric we have when we create the pipeline. We know how much data we're going to process through. And each type of worker has a certain number of documents it can process per second. So for instance, the blue ones can process 20, the yellow ones can process 200, and the gray ones can process 5. And this is where the problems begin, because the gray ones can't process 10 documents per second. So every second, the gray worker we're sending the data to, every second it's going to add 5 documents to its backlog. And every second the pipeline is up, things are just going to get worse. And so we need to do something. And so the good news is this gray worker we're looking at is processing documents independently of each other. So for instance, if maybe the role of the gray worker would be to count the verbs, number of verbs in a document. And the idea is that you don't need multiple documents to do that. You can do that bit by bit. And so this is exactly what we do. We load balance each document, the pipeline, over all the gray workers. So we send one document to one worker, the next one to another, et cetera, et cetera. And we try to keep it as homogeneous as we can. And this works really well, actually, because now no gray worker is overloaded and everything's working fine. The red worker in the pipeline is spreading the work out over all the gray workers, and then all the gray workers are sending their process documents to the purple worker. And this scales really well. If we had a second pipeline, we can just do the same process again, and it works just fine. And if we ever need to scale the number of gray workers, we can do it very easily. I mean, the math is very simple. Basically, we want the total number of documents that need to be processed by gray workers to be less than the total capacity of all gray workers. So basically, the capacity of one worker multiplied by the number of workers. And in Kubernetes, this is actually very easy to do. We call these kinds of workers stateless workers, right? Workers that can process documents independently of each other. And we can model these as three Kubernetes resources. The first one is a deployment, which contains the spec of the worker, like the container image to use, the parameters it should have, et cetera. We use a service that performs this load balancing that we do, and we use a horizontal pod autoscaler, or HPA for short, to actually perform the autoscaling I was just talking about. We can just tell it, well, on average, I want each worker to be processing 4 documents. And so if you have a metric somewhere that's telling you how many documents each worker is processing, the HPA can automatically perform the autoscaling for you. And so this is great. It's very easy to actually do. The real challenge, and the reason we really needed the operator, begins when we start looking at stateful workers. So stateful workers could, for instance, be workers that try to compare different documents in a pipeline, maybe consecutive ones in a pipeline. Maybe they're looking at the history of a document, or maybe they're looking for differences in tone in a document, or evolutions in various versions of a contract. And they're trying to compare these. And so they need to process each document in sequence. And so for any given pipeline, only one worker should be processing those documents, or at least one green worker should be processing those documents. So we can't load balance over all the green workers. So let's dive into the problem right here. Let's simplify our cluster a little bit and look at 3 types of workers. And let's suppose they're all 3 of them are stateful. So at first we don't have any pipeline. So if we want to create a pipeline, we can just create one, like pick a blue worker at random, a green worker at random, and a yellow worker at random. And this works fine. And so, well, let's keep doing that, right? Let's create a second pipeline. Let's pick these workers at random. And this is where the problems begin, because if we pick the same green worker again, because we're picking at random, we might overload one worker while we're not using the other worker. And this is very problematic. We want to optimize resource usage, right? So we want to share workers across pipelines, because that's the best way to use workers, to use resources and to avoid waste. But at the same time, we don't want to overload workers at all. So we can't pick workers at random. So at some point, if we take a step back and, all right, we have one pipeline already, and we want to create a second pipeline that will process 10 documents per second. We need some way to identify that the first green worker, the top green worker that we already are using in another pipeline, is not viable. It can only process 5 more documents per second. And so it is not viable for a 10 document per second pipeline. And once we've identified that this worker is unviable, we can simply not pick it and pick another one. And so we can place our pipeline. And so now if we try to place a third pipeline, our mechanism should be able to see that no green worker is viable. And so our pipeline is blocked. It must not be put into place. We cannot process this data. We do not have the capabilities. And so we need another feature, which is auto scaling. We need some way to scale the number of green workers based on not the number of pipelines we actually have in place, but based on the number of pipelines we need to put in place. We need to take this third pipeline into account to scale so that we can create a third green worker so that we can actually work on our third pipeline. And now we need to select a worker for each pipeline, and we need to be able to scale, but we also need resiliency. We're talking about distributed systems. Things fail all the time. And so we need to be able to fix our system dynamically in case of failure. So let's imagine, for instance, that we have a yellow worker that fails. Right now, 2 of our pipelines are not going to work. Right? 2 of our green workers are going to try to send documents to the dead yellow worker, and that's not going to work. And so if we know, we need some way to actually know that the yellow worker is unhealthy, and then we need to fix the pipelines. We need to reconfigure the green workers so that they send their documents to a new yellow worker, right? And then the yellow worker itself needs to be able to notice, oh, these are new pipelines, but they already existed. Let me go download the cache that the old worker was using so that I can take this work on now. And so we have 3 functional requirements. We need to be able to select viable workers for each pipeline. We need to be able to scale the number of workers based on load, and we need to be able to react to changes in worker status. That's it. And that's why we need the operator, because Kubernetes doesn't do this natively. That's a problem. And so we need to extend Kubernetes, the abilities that Kubernetes has in order to actually build a platform that does what we want. So let's have a quick look at what we used to actually build this operator. The first thing that we did is created new custom resources, define new custom resources inside the Kubernetes API. So Kubernetes has this great feature which allows you to define what we call custom resource definitions, or CRDs, just like any other Kubernetes resource. So you can create a deployment, you can create a service, but you could also create a CRD. And what a CRD does is it defines the spec and the status of a new resource. And once you've created your CRD, Kubernetes is able to actually handle these new types of resources. And so what we did is we defined a new pipeline resource, a pipeline binding resource, and a worker class resource. And so let's talk about what these actually represent. Well, the pipeline resource actually just represents a desired pipeline, like a user wants this pipeline to exist in our system. And so usually this pipeline will contain the number of documents per second we need to process and which types of workers need to process these documents and in which order. A pipeline binding is not something that it will actually be user facing, right? This is how the operator persists decisions it's made. For instance, when we create a pipeline, the operator needs to select a blue worker, a green worker, and a yellow worker. Well, it's going to create one binding per choice. So it's going to create one binding that assigns one blue worker to our pipeline, one binding that assigns the green worker to a green worker to our pipeline, and one binding that assigns a yellow worker to our pipeline. And this allows the operator to actually look up past decisions it's made and use them to actually make future decisions. And that way we can guarantee that we are working in a consistent system and that we have all the information we need to respect the constraints we want. And finally, the worker class resource is purely metadata. It doesn't actually represent anything. It just contains information on our different worker types. So for instance, well, actually the only information it contains for now is the number of documents per second that a given type of worker can process. And so the operator is going to use this resource to look that up. And so the operator doesn't actually need to have an exhaustive list of each type of worker in its code. It just looks up all the worker classes in your Kubernetes API and works with those. So that way it's very dynamic, it's very extensible, and the whole point is that we wrote it once and we haven't touched it since. And so once we have those, we've designed and we've chosen these CRDs, we used a framework called KubeBuilder. And so KubeBuilder is a framework for building operators, for writing operators in Go. And so it's written by some of the core Kubernetes developers. And so it uses the same code as Kubernetes. And what's great about KubeBuilder is that it just generates code for you so that you can just implement the features you want. It handles all of the plumbing for your operator. And so it really simplifies everything. And I highly recommend using it. I'm not going to go into the details of how KubeBuilder works, but if you want to look into it, I highly recommend it. And then another core component we used to make our operator work is Prometheus. Like I said, we need to scale the number of workers we have based on metrics, and so the operator needs to expose these metrics. And so the operator actually, based on all the pipelines it has, all the pipeline bindings it has, it can actually compute how many documents each type of worker is supposed to be processing in total. And so it actually exposes these metrics to Prometheus, so Prometheus can come and scrape them, and then we can inject these metrics into the Kubernetes API and plug our horizontal pod autoscaler onto them. And so we get autoscaling based on the number of pipelines we've actually declared. And so to compute these values is actually very simple. The operator, for instance, if it wants to compute the number of, it will simply list all the pipeline bindings it has that regarding blue workers, and simply sum the number of documents these bindings actually represent. That's it. And just by simply making this list, and every time, so by simply calculating this sum, every time we create a binding or we delete one, and just keeping these metrics up to date, we can build a very reactive auto-scaling system, which we can just simply plug into the core Kubernetes horizontal pod autoscaler. So we didn't need to implement our own autoscaling, which was a relief, to be honest. Plus, the Kubernetes autoscaling features actually work really well, so we might as well use them. And that's all we built the operator with. So it's actually not that complex a component. It doesn't have many dependencies. So let's get into how it works. So the first feature we needed was to select viable workers for each pipeline, right? So if we go back to what we had before, the cluster we had before, we had 3 types of workers, right? So we had blue workers, green workers, yellow workers. This is modeled inside the Kubernetes API by 3 instances of a worker class, right? And each worker class contains the number of documents that each type of worker can process. And so these values aren't actually going to change over time, but the operator is going to use them constantly to make decisions. And so if a user decides, all right, declares, all right, I want a pipeline, they simply create a pipeline inside the Kubernetes API. And this is where the operator comes into gear. The operator reacts to events on this pipeline resource. So whenever a pipeline is created, updated, or deleted, our operator has a handler that gets called. And this handler will do all the work necessary for the pipeline to come into place. And so the first thing, so when you create a pipeline, for instance, this pipeline is called first, and it's going to process 10 documents per second. When you create it, its status is pending, right? So the user knows, all right, this pipeline is not ready yet. It's not going to process data yet. But so the operator sees this pipeline and creates 3 bindings. It selects 1 blue worker, 1 green worker, 1 yellow worker, and persists this choice as a binding in Kubernetes. And so these bindings are still pending, because when we create a binding, we actually want it to result in specific configuration inside Kubernetes. And so for each binding, we actually create a service. And so a service is a native Kubernetes resource that it's a network abstraction, basically. You can send a request or a document to a service by name, and the document will actually arrive to one of the workers. Precisely, it'll arrive to the worker that is in the service's endpoint, or that is the service's endpoint. So basically, if you send a document to first blue, it'll arrive to blue 1. And if you send a document to first green, it'll arrive to green 0. But the thing is, you don't actually know which worker you're sending the document to. And the point is that you don't need to. So the operator decides which worker is going to process data for each pipeline. So all you need to know is the name of the service to use. And so we create these services. And once these services are created, the bindings, their status is, the operator updates the status of these bindings and marks them as ready. And once all the bindings for a given pipeline are ready, the operator updates the status of the pipeline to ready. And so we now the user knows, all right, this pipeline is ready, it's ready to process data. And so the user can send a message to the first worker in the pipeline, so here the blue one, telling it to start sending data down the pipeline. Now, if we add a second pipeline, so the user creates a second one. And so this pipeline, as the first one, is pending at first. And so the operator sees this pipeline and needs to create 3 bindings, but it needs to select workers. And the operator can look at existing pipeline bindings, right, and see that the first green worker is already used in a pipeline and doesn't actually have enough capacity left to process the second pipeline. So it's simply going to select the other green worker. And once these workers are selected, the 3 bindings are created in the Kubernetes API. So these bindings are pending, and the pipeline status is updated to plotted, because it's not ready yet, but still it's in progress. So it's decisions have been made. We're just waiting for the bindings to actually result in services before we start sending data down the pipeline. And so once we create these 3 bindings, we create 3 services. And once the services are created, the bindings the binding status is updated to ready, and then the pipeline status is updated to ready, and we can start sending data. So this is basically how the operator works. I mean, this is how it selects workers for each pipeline. It's not a very complicated process. I mean, the key insight is to persist the operator's decisions inside the Kubernetes API. The operator itself is completely stateless. You can turn it off and turn it up again, and it'll know exactly what it's done beforehand by simply listing all the bindings in the Kubernetes API. And one advantage of this feature, of this implementation, is that right now we're talking only about stateful workers, but if we have a look at the stateless workers from before, the only difference in our implementation is that instead of the services we create having only 1 endpoint, they have a list of endpoints. And this list of endpoints is simply every single worker of the desired type. So for instance, if you send a document to first gray, then you will, the document will be processed by any of the gray workers. We don't know which, and the point is we don't care. We know that each worker is going to process these documents in exactly the same way. And so we can simply, a red worker can simply send a document to first gray. Maybe it'll be handled by the 3rd gray worker. And then once that gray worker has processed this data, it can send the document to first purple, which happens to be the middle purple worker, but the gray worker doesn't need to know that. So our implementation is actually very flexible. It works perfectly for stateful workers and stateless workers with very little differences. Now onto the second feature, which is that we need to scale the number of workers based on load, right? So if we, now at this point, we're not going to look at pipeline bindings and services anymore because they aren't really relevant to this feature. Instead, we're going to be looking at horizontal pod autoscalers. So if we look at this example, we have, right, where we have 3 stateful worker types and 2 existing pipelines. We have 3 worker classes that correspond to each type and 2 existing pipelines that are in ready status. And so we have 3 horizontal pod autoscalers, 1 for each worker type. And so each of these pod autoscalers is going to aim for an average of 70%, say. That's usually what the value we went with, although it could vary. And the autoscaler is going to aim for each worker type to be, on average, at 70% capacity. And so right now, the situation is pretty much stable. Actually, the horizontal pod autoscaler could downscale the blue workers and the yellow workers because we don't need to have that many. And so if we actually waited a few minutes, it actually would do that. But the point is, right now, this situation could actually perfectly happen if you recently deleted some pipelines. And so right now, if we declare a 3rd pipeline, this pipeline is going to stay pending because there is no viable green worker to select. And so the operator is simply not going to create any bindings and is going to leave this pipeline as pending and is simply going to check again a second from now. And so it keeps checking every second. Basically, it's waiting for the horizontal pod autoscaler to do something. And so in the meantime, the operator has exposed through metrics the fact that it needs more power, more total capabilities from the green workers. And so the horizontal pod autoscaler for the green horizontal pod autoscaler suddenly realizes it is not at 66% of its, it's not at 66, it is not at 66% capacity on average anymore. Now it is at 100%, which is over 70. So it's going to scale up, and it's going to add a third worker, allowing the operator to select it for this new third pipeline. And that's how auto scaling works. Basically, we just manage to plug the operator onto the Kubernetes core auto scaling features. And so now for the last, well, third and last feature, which is to the operator needs to react to changes in worker status. So this is the situation we have, and so we don't need to talk about horizontal pod autoscalers right now, but we do need to look at pipelines and pipeline bindings, because the idea is that if we lose a yellow worker, the operator needs to react. And so when a binding has selected a pod that is unhealthy, the operator updates the status of that binding to dead end, right? This binding doesn't lead anywhere. If it's used in a pipeline, that pipeline is not going to work. And in fact, because two of our pipelines have a dead end binding, their status is actually updated to broken, which signals to the user that they need to stop sending data down this pipeline. It's not going to work for now, right? The operator needs time to fix this pipeline first. And actually, once a pipeline is broken, the operator undoes all bindings, right? It unsets all bindings for these pipelines, right? This is to make sure that pipelines that aren't actually doing anything because they're broken aren't actually being taken into account when other pipelines are being processed. So if we have a broken pipeline, this is not stopping us from actually keeping the other pipelines working. We can actually still continue creating other pipelines. The operator works very concurrently. And so once all the pipelines have been cleaned up, all the broken pipelines have been cleaned up, the operator can start trying to fix them. And so the way it fixes them is simply by selecting 3 new workers. It starts the process over entirely. And so it selects 3 new, 1 blue worker, 1 green worker, 1 yellow worker, updates the 3 bindings. It doesn't create new bindings, just updates the old ones, and updates the status of the pipeline to plot it just like before. And so once the bindings are ready, the pipeline comes back to a ready state, and the data processing can continue. So let's see that again for the second pipeline. We select new workers, update the pipeline bindings, right? And these are going to update the configuration of our services in the background. But this is abstracted away because the operator is handling that, but it's another part of the operator. One part of the operator is handling creating the pipeline bindings, and another one is handling reacting to the pipeline bindings. And so once the bindings are created, the services are going to get created, and the bindings are going to switch to a ready state. And once that happens, the pipeline switches to a ready state. And so the operator actually is able to fix existing pipelines in case of incidents. And so this in production, this happens in less than a second. So when we lose a worker for some unknown reason, we interrupt data processing for less than a second, and then we start again. And so the whole point was that we wouldn't simply be sending data down a broken pipeline. We actually know that we need to stop data processing because the pipeline is not going to work. So we were actually able to identify any documents that we haven't processed and then process them later. So we don't lose any data. And another nice ability of it, a nice combination of 2 of our features, so auto scaling and this resiliency, is that when our horizontal pod autoscaler decides to downscale and so deletes a worker because there are too many considering the number of pipelines we actually have, and the idea is that this worker its status is going to be set to terminating in the Kubernetes API. So this is actually a Kubernetes feature. We did not invent it. And so this worker will be in terminating status. And so the operator will immediately flag all bindings that use this worker as dead end. And so fix all pipelines. And actually, when that happens, the worker still actually works. Even when it's in terminating status, it's not off yet. And so we actually don't stop processing any data. The operator has time to just fix every pipeline that the worker that was using that worker, and we actually don't stop processing data at all. And so that's how the operator works. I hope you were able to follow. I don't think it's very complicated, but I wrote it. So, I mean, that makes sense. But the idea is that if you keep it simple, if you keep it modular, and if you model your problem correctly inside the Kubernetes API, it's not that complicated to write an operator. And so let's get down to, well, what was it like to actually develop an operator? And the first thing I need to say is that making an operator that works requires a deep understanding of Kubernetes. You are essentially writing Kubernetes controllers, right? So this is how, I mean, the Kubernetes control plane works with controllers, right? That are in constant loop to reconcile a desired state with the actual state of your cluster. And you need to understand this process. You need to understand that controllers are what we call finite state machines, in the sense that each resource can move from one state to another, and that these transitions are very well known and documented. And if you understand that, then you can write your own set of controllers. And this set of controllers that make your application work is what we call an operator. And so, like I said, we're working inside a control loop, all right? And so a good practice, if you decide to write your own operator, and this is friendly advice, let's call it that, is to, at every loop, basically, you'll be looking at, say, a pipeline or a binding, or a pipeline or a binding, and you'll be comparing the spec of your resource to the state of your cluster, and trying to find any action you need to take, or your operator needs to take, in order to change the status of your cluster so that it matches your spec. And if you're updating, and in that same loop, you will be updating your resource's status. And a good practice is to recompute that status entirely at every loop based on the resource's spec and the cluster state, and nothing else. Do not use the status to compute the status. That is a recipe for disaster. You need to be able to recompute your entire status from scratch every time. Another big thing during development was that this operator is written in Go. So KubeBuilder generates a lot of scaffolding, a lot of code that you can just fill in to develop your operator. And this code is in Go. So you have to write your operator in Go if you want to use KubeBuilder. On this project, we had one experienced developer who had 2 years of experience of writing Go, and one beginner who only had a few weeks of experience. And this wasn't a problem. Writing Go is surprisingly simple, and KubeBuilder handles all the complicated things. It handles caching. It handles requests to the Kubernetes API. It handles queuing resources if multiple come in at once. All you need to implement is a handler. And that's actually not that complicated. All you need to implement really are your business features. And a big advantage of actually writing your operator in Go is that Kubernetes is written in Go. And so KubeBuilder actually uses the same code and the same libraries as Kubernetes does. And so out of the box, you get really, really powerful features that Kubernetes uses every day. You get that inside your operator. And that's amazing. And it's honestly really worth it. Another, something else we did during development was that we developed mock workers. So we didn't actually use real the real production workers during development. The reason for that was that some of these workers actually use AI and are very resource hungry, and so you can't start a lot of them on your development laptop. And so we developed lightweight versions of the workers we used in production that basically were simple HTTP servers that simply sent each other payloads, because the operator didn't need to know much more than that. And this allowed local testing of operator features, because we were able to start tens and tens of workers locally, which allowed us to test what happens if we break a pipeline, if we create too many pipelines, to test auto scaling, et cetera, et cetera. And most importantly, to test the operator's performance, because that way we had workers that started extremely quickly. They started in under a tenth of a second, which allowed us to actually see, well, how fast is the operator itself? Because when we use it with production workers that take several seconds to start, it's hard to realize, well, how fast is the operator itself, or is the speed we're seeing really just a consequence of the workers we're using being slow? And so we actually were able to perform benchmarks, which allowed us to determine that when the new pipeline was created, it took less than 2 seconds to have it in a ready status and to be able to start processing data. And if we had a pipeline that was broken, the operator was able to fix it in under a second every time. And so in our local development environment, we actually needed a cluster, because we needed to deploy the Kubernetes operator into this Kubernetes cluster with a fully functioning Kubernetes API and all of its controllers. And we also needed to deploy our workers inside that cluster, because the operator assumes the workers are pods. And so what we used was Kubernetes in Docker. If you don't know Kubernetes in Docker, it runs Kubernetes inside Docker containers on your machine. So this is great because it's actually really fast to start. You have a cluster up and running on your machine in less than a minute, and it's actually really amazing. One advantage I found in Kubernetes in Docker, or KIND for short, is that unlike Minikube, which is an alternative, KIND is able to easily manage multi-node clusters. So the idea is that if you want 3 nodes, if you want to simulate 3 nodes in your Kubernetes cluster, you can tell KIND to do that, and it'll simply start 3 Docker containers, and each container is going to be a node. And this was great because it actually allowed us to test what happens to the operator, or how the operator reacts when we kill a node. So what we did was we started 3 containers, and then we just shut down one of the containers to see what happened. How did the operator react? How did Kubernetes react to workers simply disappearing from the network? So this was great to actually test resiliency. And KIND is also great if you want to use it in continuous integration. In your CI/CD system, you can start a cluster with KIND, deploy the operator to it, deploy your workers, and run some automated tests. And that works really well. Another big advantage of KIND is that it uses kubeadm to actually set up Kubernetes. And so kubeadm allows you to easily enable Kubernetes alpha features. And we actually used one that I didn't mention before, but when we actually enabled auto scaling for our workers, we were able to scale down to 0 workers if these workers were used in no pipelines for the moment. And that allowed us to save tremendous amounts of resources, because we had tens and tens of different types of workers, and the fact that we actually needed to have one of each running at all times, even if they were unused, was wasting a lot of resources. And so scaling down to 0 actually allowed us to save a lot. And one last feature I want to talk about for KIND, and probably my favorite, is the KIND load command. So when you're developing locally, you're going to compile the operator, and you're going to package it inside a container as a container image. And then if you want to deploy it to your local Kubernetes cluster, if you're using Minikube, what you need to do is you need to push your image to a registry, and then from your Kubernetes cluster, local Kubernetes cluster, pull down that image. What KIND load does, it copies the image that you have on your local machine into the cluster running on your local machine. And so that's a real time saver and avoids pushing countless images to your registry. And so what are some lessons that we learned and developing this operator? And my goal for this section is really to share some insights that I think might actually be important to you if you're considering writing an operator. And the first one is that the operator does not scale horizontally. Only one instance of the operator can create or update resources, custom resources at once. You can't have two instances of your operator selecting workers for a same pipeline at once. That's not going to work, and you're going to have a really bad day if you try to do that. So the good news is that you can still have multiple instances of your operator running, but it's just only one of them is actually going to be doing any work. The other ones are going to be in a passive state, simply waiting for the operator that is the instance that is actually working to fail so that they can take over. And so this is implemented as a lock that the operator creates in the Kubernetes API. And so when it starts, it tries to take this lock. If the lock is free, it takes it. And so it knows that it's allowed to do work. But if the lock is already taken, then it's simply going to wait for the lock to be released, and it's not going to do anything. So we still have high availability, but you can't scale horizontally. You can still scale vertically, but and what we saw was that the operator actually doesn't use that much CPU. It can use quite a bit of RAM because it keeps a cache of all your pipelines and pipeline bindings and services and pods, etc., locally to avoid creating too much load on the Kubernetes API. So it can use quite a bit of RAM, but that was never a problem for us. The operator was never actually a scaling bottleneck. Another insight is that services have a cost. If you notice, you may have noticed during our architecture that if we create thousands of pipelines, we're going to be creating tens of thousands of services, and that actually has an impact on your performance. What we noticed is that if you have too many services in your cluster, and when I say too many, we started seeing an impact on performance around 2,000 or 3,000. What happens is every single TCP request that goes from pod to pod in your cluster actually slows down a little bit. There starts to have some latency. And so an easy way for us to optimize for that is that we changed our model a little bit to reduce the number of services we were creating. And something else we did was simply start to divide our platform into multiple clusters, and so that different groups of users were using different clusters, so that we didn't have too many services in any given cluster. And something that's another thing to note is that if one worker is sending a document to another worker and it reuses the same TCP connection, the service cannot perform load balancing. The services perform load balancing only when the TCP connection is opened. And this is something that surprised us a little bit when the operator simply reconfigured a service expecting all new documents to be sent to the new worker it had selected, but some documents kept being sent to the old worker. And this was because some workers weren't recreating their TCP connections. So what we did to fix this is simply we configured all the workers to actually never keep TCP connections longer than a certain time. That way, when we reconfigured services, we had a guarantee that after X seconds, the connections would be renewed and that load balancing would be taken into account. All right, so this is not something, well, this is something we knew. Services can't select pods by name. So if you've ever actually used services in Kubernetes, you know that services perform load balancing over a set of pods that you select with labels. And you can't select the pod by name. And in our models, often we needed to create a service that only pointed to a single worker. And so what we had to do is for those workers, for those stateful workers, we needed to deploy them using stateful sets, because stateful sets add a pod name label containing the pod's name. And so you can use that label in your service to load balance only to a specific pod. For stateless workers, deployments were enough, right? Classic deployments in Kubernetes don't have this label, but they work perfectly. A problem we had is that stateful sets aren't perfectly equivalent to deployments, and so sometimes it was problematic. Stateful sets give you some guarantees that we didn't need, and that actually created some problems for us. And so a solution that we thought about and that we actually didn't end up doing in the end was to implement a new custom resource called a worker set that would, for starters, replace the worker class that would contain the same information as the worker class, but it would also be responsible for actually creating the worker pods instead of using deployments and stateful sets as we usually did. And the only difference, it would be a re-implementation of a replica set or a deployment, but the only real difference would be that it would add a pod name label to each pod, and because that's all we needed. We didn't do it in the end though, but we could have. That's what we learned with the operators, that actually implementing new resources like this is surprisingly easy. Of course, you're working with when you're working with concurrent distributed systems, something you need to be aware of is race conditions. The operator handles different resource types concurrently. So for instance, it could be reconciling a pipeline at the same time it's reconciling a pipeline binding. And so you need to know this to be sure, you need to take this into account so that you're sure you don't create any race conditions in your code. But the operator does give you one guarantee, is that when it, for instance, if you're handling pipelines, it will handle each pipeline sequentially. So you won't be actually, so the operator is never actually selecting workers for two different pipelines at once. So what we needed to do was, when we're handling a pipeline and we're selecting workers, we need to be sure that by the time our handler returns, that we've created the bindings responsible for, the bindings that correspond to the operator's choice inside the Kubernetes API before we return. This was very important. Otherwise, we would have race conditions, which is terrible. And another thing to be careful about is deadlocks. This is not specific to actually developing operators. Deadlocks can happen for a variety of reasons, but basically, the problem we have is when we create a pipeline and there aren't any workers that have the capability to do so, the operator leaves the pipeline as pending. And if the horizontal pod autoscaler doesn't scale, well, then that pipeline will stay pending forever. So we had a workaround for this, which is that mathematically, you can prove that if the margin that the horizontal pod autoscaler has for each pod, so for instance, when we said we were aiming for 70% capacity, so if the remaining 30% is greater than any number of documents per second that a single pipeline will try to process, then you can't deadlock. So that was good. That allowed us, so our fix was, when pipelines came in, we made sure that they didn't, that the number of documents per second they were going to process didn't go over the 30% of capabilities for each type of worker. And so that actually eliminated our problem. But beware of this kind of situation when when you have part of your algorithm that says, okay, I'm going to wait for something else to happen, and the other part of your algorithm is also waiting for something else to happen. Make sure you don't have a conditional loop somewhere. And finally, last lesson we learned was that the operator can implement what we call validating and mutating webhooks. So what these are these webhooks get called by the Kubernetes API when a custom resource gets created or edited or deleted. And so this allows the operator to actually check that the resources you're creating or that you're putting into the Kubernetes API are valid. And if it wants, it can actually even change them. So we use this to make sure that, well, for instance, I was talking about the fact that pipelines have a maximum load depending on the processor types they use. Well, we used these webhooks to validate that. We also used the webhooks to validate that pipelines didn't have cycles in them, because that would be problematic and should never happen. And we actually never had well, the operator just checks that pipelines don't have cycles in them. A problem with this, well, not a problem, but a trade-off with this is that now the Kubernetes API depends on the operator. So if the operator fails, the Kubernetes API is going to fail for these custom resources. And if the operator is slow, the Kubernetes API is going to be slow for these resources. So that's something to take into account. Also, these webhooks get called every time a resource is created, updated, or deleted, which creates significant load. So if you don't need these webhooks, maybe you shouldn't use them. And finally, these webhooks didn't run while we were developing locally and the operator was running outside our cluster. So we actually, to test these webhooks, we actually needed to package the operator inside a Docker image and deploy it into our local Kubernetes cluster for the webhooks to actually work, which was the only feature we actually needed to do that for. For every other feature, the operator is fine just running outside your Kubernetes cluster as long as it has access to the Kubernetes API. And so now for the overall experience of actually developing an operator, the first thing I want to say is that it was absolutely worth it. The operator is very fast and it's reliable, and adding new behavior to it is surprisingly easy. The most time we spent working on this operator was actually just getting up to speed on how it works and how KubeBuilder works and how we should structure our code. And there was a lot of design, but the idea, there was a lot of time we spent on design and determining that we wanted a pipeline binding, and worker class, and things like that. But now that we actually know how to write an operator, we're seeing opportunities to write some everywhere because it's surprisingly easy. If we wanted to rewrite this operator from scratch, it would take us a couple days, and that's it. And that's not very long to develop such a powerful piece of software. Another thing I really want you to know is that KubeBuilder is great. It handles all the plumbing, and we measured, and of all the time we spent actually writing code, 95% of it was spent implementing features we wanted. The remaining 5% was usually editing Kubernetes manifests so that the AE operator was deployed in a specific way that matched our platform. But 95% of our time was actually spent bringing value to our platform, and that's amazing. Like I said, like I mentioned before, there was a significant design phase to choose which custom resources we wanted because you're making these up. So you need to make sure the choice is actually correct. And we iterated a lot on this part. Basically, you're designing a finite state machine. So you need to be able to list every possible state and every possible transition between these states. And turns out this can be very complex and not that easy to do. We didn't have much experience doing this. And this is basically in the realm of software engineering, but just take this into account. It's a real puzzle. And so the real question is, should you build your own operator? And the answer is yes, if you have specific scheduling needs. If you can deploy your applications inside Kubernetes and they work fine with core Kubernetes, then you probably don't need an operator. On the other hand, if you're finding yourself using weird hacks to get your applications to work inside Kubernetes, or that you find that you have trouble automating every part of your application's lifecycle, then an operator is probably the answer. And so the operator is really perfect if you have stateful applications that are running in Kubernetes. These can be databases, or they can be data processing pipelines that simply are stateful in their nature and the way you want to use them. And so the operator really is great for that. And so if you decide to build an operator, please let me know, because I'm highly interested. I believe that we are on the cusp of a huge wave of new operators coming in. The open source community has already developed many for open source projects, but what I predict that we are going to see new Kubernetes operators arriving for non-open source projects that we develop every day. And I hope that once you develop your operator, you will be as satisfied as I was. Thank you.